Hey guys, welcome back. Today's algorithm is merge sort. Merge sort is based on the divide and conquer paradigm, in which a problem is recursively broken down into subproblems until a trivial case is encountered. At that point, the trivial case solutions are gradually pieced together, yielding the solution to the original problem. For our task, the trivial case is a single element, because a one-element list is already sorted. Numerous implementations of merge sort exist, but today we're just focusing on the standard version, referred to as top-down merge sort. As usual, let's visualize this concept using an unsorted set of cards. The first step is to divide the cards in half, leaving us with two new sets. Next, do the same to the left half. This results in two instances of our desired trivial case, a single element. Now we need to merge those cards back together, sorting them as we go. 4 is less than 7, so 4 is placed first and 7 follows. Time for the right half. Split that set and we have the same scenario as the left side. We know that 6 is smaller than 9, so 6 is moved first and then 9. With two newly sorted sets of cards, we're now ready for the last step, which is just repeating the merge process for the original set. 4 is first, then 6, then 7, and finally 9. There you have it. Simple, right? Now for the C++ implementation. We'll use this array of 5 cards for the example. Recursion can make following along with the code a bit difficult, so I'll color the current recursion level blue. Let's start out by adding a base case that checks if there are less than 2 elements. If not, find out where to split the array by dividing n by 2 and assigning that as the size of the left portion. In our case, integer division gives us 2, so the right side will have a size of 3. We can now create two auxiliary arrays using the calculated sizes. After that, populate the arrays using for loops, first left, then right. That concludes the first split, so now we have to repeat the same process for the two new arrays, which brings us to our first recursive call. Left is up first. Stepping into the method again, we start by checking the base case. This array is size 2, so we proceed with the split process. Calculate the left and right sizes, allocate the new arrays, and populate them. Once again, we find ourselves at the recursive call. But this time, there's only one element, so we return immediately. Since we can't go left any further, it's time to check the right side. It too only contains one element, so again, we return after the base case. Now we can start merging back together by stepping into the merge function. The first parameter is the parent of left and right, the one highlighted in blue. We start by declaring 3 indices to keep track of where we are in each array. Next, we enter a while loop that continues to execute until either the left or right array reaches the end. Because if one side reaches the end, we have nothing to compare the other side to. In this case, we can see that left index is less than left size and right index is less than right size, so we can enter the loop. Inside the loop, we check if the left element is less than or equal to the right element. 3 is less than 5, so we place that in the first slot of the parent and increment both parent index and left index. On the next iteration, notice that left index is not less than left size, so we break out of the loop. Now we need to find out which side still has elements remaining so we can put the rest of them in the parent. Left is empty, so we check the right side. The right side contains the 5 of clubs, so it's moved to slot 2 in the parent. Our first merge is now complete. Okay, so we've returned to the merge sort function and we're ready to exit this level of recursion. But notice our two auxiliary arrays are still taking up space on the heap. Before we go any further, we need to deallocate those arrays using the delete keyword with brackets. There we go, that's better. Back to recursion level 0, the very first merge sort call. With the left side taken care of, the next step is to recurse on the right side. This array is size 3, so we pass the base case and proceed to split the array. Call merge sort on the left side, and it returns immediately. Call merge sort on the right side, and we find that we have some more work to do. Split the array, recurse left, only one element, so that returns. Recurse right, only one element again, so that returns as well. Okay, no more splitting arrays. It's all merging from this point on. Step into the merge function, declare the indices, and enter the loop. This time the right side contains the lower element, so it's moved first. Right index has reached the end, so we break out of the loop and add the remaining element from the left side to the parent. Back in the merge sort function, delete the temporary arrays and return to recursion level 1. Next up, yep, you guessed it, back to the merge function. Enter the loop. 2 is moved first, then 3, and then 9. Delete the temporary arrays and return to recursion level 0. We're now ready for the final merge. But first, take a moment to observe that prior to any merge, both left and right sides are completely sorted, which all started with the single sorted elements at the very bottom. All we're doing is maintaining that sorted quality on the way back up. So back in the merge function, 2 is moved first. For the next comparison, both values are equal, so the one on the left, the 3 of diamonds, is moved first because of the less than or equals operator. This detail is important because it allows merge sort to be a stable algorithm. I'll talk about that a little more in the follow-up analysis video. The next card to be moved is the 3 of clubs. Then 5, exit the loop, and finally 9. Back at recursion level 0, delete the temporary arrays. And we're finished. The cards are sorted. I'm sure you're thinking, wow, that was a lot of work for such a small list. And you're exactly right. This algorithm is not efficient for small lists. Insertion sort is a much better option for cases like this. The real potential of merge sort shines when sorting large lists. We'll get into that in the next video when we analyze time complexity and other qualities of merge sort. See you guys then. Thanks for watching.